Okay, sounds good.
Right. So if I add up all the probabilities of the rolling of a die, of anything, if I add up the probabilities for any situation, they have to come out to be what? 1. It's got to come out to be 1. Just like, and another way to look at probability is it is relative frequency, right? All the relative frequencies have to add up to 1, or else we did what? We left somebody out. We rounded maybe, but I'm talking, when I say add to 1, I mean if you don't round. Yeah.
I don't understand.
All right. What's if the probability is going to rain today is 1%? What's the probability it's not going to rain today? How do you know that so quickly? Because you know all the probabilities have to add up to be 100%. We know that. In any given situation, if I add up all the probabilities of all the things that could happen, it has to come out to be 1 or 100%.
Yeah, I think you added up all the numbers, so it would be 1.
Held. So not the numbers, but the probabilities. These are events.
Yeah.
So the probabilities of those events have to add up to be 1. How are we doing so far?
Good.
All right, so nothing major there, really. In fact, you guys know that intuitively until I say it like this. And I have to say it like this to do some of the stuff. So let me say that a little more specifically. Oops, not 0. Way too specifically here, right? But just deal with it. That's what we're saying. You really want to write the whole damn thing out. With me? Yeah. So there's a reason I'm writing it out, and let me actually make a little bit better problem here to go where I want to go. Let's say I ask people how many kids they've got. Number of kids. So let's say I get, some people have no kids, some people have 1, 2, and let's just say the most I saw with the people that I talked to was 3. You guys with me? I know people have more, but not from who I talked to. And let me see if I just make this and you guys are cool with this. We've seen tables like this before. So obviously now I'm going to list the probabilities for each one of these. So say 10% of the people had no kids, 35% had 1 kid, 30% had 2 kids, and what's this got to be then?
25.
Good, you're with me. Right? They got to all add up to be 100 or 1 for a decimal. So this has got to be 0.25. Okay, so far so good, right? Now here's kind of a silly question. Here's an excessively silly question. What's probably I pick somebody who has 2 kids?
1 out of 30 or 30%.
30%. Now I'm glad you said the first thing. It's not 1 out of 4, for example. You don't say there's a 1, 2 out of 4 numbers. You have to refer to their probabilities. Are they all equally likely? No, it's not equally likely to find somebody who has 0 kids as it is to have 3 kids. You with me? So probability of 2 kids would be 30%. Now, in this case, this is a very simple question, but I'm going to hopefully have you with me. One of the most important little questions for some of these questions is, what's probably at least 1? Now, there's 2 ways to do this. What does at least 1 mean? How many kids would somebody have to have?
1.
1 or 1, or in this case, 2 or 3. I'm with you. So 1 or more is fine, but 1, 2, 3. You with me? So what would that be?
90.
Now, do some of you guys, now you can sit there and go 0.35 plus 0.30 plus 0.25, 0.90. Anybody see a better way to do it?
Subtract.
Yeah. So right there, now hold on to what you just said. Does that make mathematical and even maybe just normal general sense? Right? Of course I wouldn't add. And imagine, what if I had kids, people had kids up to like 20 freaking kids. I'm talking to farmers and they had to make kids so they can go out there and work on the fields. 0 through 20. And I said, probably at least 1, you got to add this and this and this and screw it and screw it. No, let me just do 1 minus this. Are you guys with me? Of course it's got to be 1 minus this. All of these add up to 1, right? So to figure out what this adds up to be, it's got to be 1 minus that. that would be what the rest is. You with me? Nothing major there. So anytime I see the probability of at least 1, when it's like 0, 1, 2, 3, that will be equal to 1 minus the probability of none. Now that would so kick ass if my list was long as hell. Instead of adding up all these, I just do 1 minus the single thing there. That's going to be awesome. So the probability of at least 1 could mean a lot of calculations. Here, 1 calculation. Right? Okay, hopefully I got you on board here a little bit. There's a more general idea. This is the more specific thing that happens a lot. Let me see if you guys are cool with this. What would the probability of at least 2 be? How could I turn that around? At least 2 would be 1 minus none or 1. In this case, that would be kind of stupid. But again, if I had 100 things listed here and I said at least 2, instead of adding 2 to 3 to 4, adding up all those probabilities, I could just do 1 minus these 2. Okay. You guys semi with me? All right, so the more general idea here is the one that I said earlier about the rain and the no rain. So probability of rain plus probability of not rain, which I'm going to call this, a little bar overhead. That means not, right? Somehow it's better than writing the word not. So that's going to have to be what? What do those have to add up to be? 1. And we know that intuitively. That's why when I said 1% chance, you're like, 99% chance is not right. Okay. So in general, the probability of an event plus its opposite, which probability is called its complement, is 1. And the word complement kind of makes sense here. It complements each other. Together they fill each other out in 1. However you want to remember that. How are we doing so far? I'm sorry, do it again?
I get those numbers.
Here?
Yeah.
I made them.
Oh.
Totally, yeah. There's nothing up here that you could possibly use to get those. So you're right. This is a situation that you'd be given. Or I tell you, 7 people had no kids and 20 people had 1 kid, and you have to make up your own probabilities by dividing, make relative frequencies, right? So you could certainly make this list if you had to. I have to give you the information, though. Okay. So what about... let's see, what else I got to tell you. So far, so good? Does this make sense? Is that all right? These probabilities are not evil. They're not really evil. You're good?
Yes.
Okay. Up here, let me take that. A couple of definitions I have to tell you about. So think about that for a second. Mutually means you both do something. So you both, mutually you exclude each other. Mutually exclusive. All right? If I am a dog, I cannot also at the same time be a cat unless you're watching old cartoons. So mutually exclusive means exactly that. None of A are also in B and vice versa. So if 2 things are mutually exclusive, so for example, there's dog, cat, ice cream, rock. So I like it. Ice cream? Not ice cream. That's how you boil the world down. You are not ice cream. Get out of here. What must be true? So if I have A and B, 2 events that are mutually exclusive, can you tell me something about them probabilistically? Make up an edge. So something about their probabilities. What must be true then? You can't tell me a damn thing about this or this. I don't know. But you can tell me something about that, of course. That one's simple. So, for example, from cards, heart, clubs. Are those mutually exclusive? If I have a heart in my hand, a heart card. What's probably I have a club in my hand? Well, 0. It's gone. There's no chance. You already told me it's a heart, Jeff. That's crazy. So what's the probability of A and B then? 0. Cool. Right? So mutually exclusive just means that none of one is in the other one. So if I said hearts and kings, is that mutually exclusive? Careful. Because there is a king that is a heart. So if they ask you, are these mutually exclusive? Think to yourself, is there something here that could also be this? So if I said a male under the age of 30 and a nurse at a hospital, are those mutually exclusive? Because there is, I'll bet you anything, there's a male nurse under the age of 30 somewhere in the world. You with me? Okay, how are we doing so far? That's how you approach the problem, though. You think to yourself, is there one of these that could also be this? If so, it's not mutually exclusive. Right? If there is nothing, then it is mutually exclusive. If there's no way it could be both. Yeah.
Is there a way to be unmutually exclusive, I guess?
Well, of course, yeah. I mean, what do you mean, like, not mutually exclusive? Like we just said, king and heart. Oh, it only excludes in one direction, no.
Oh, okay,
Yeah, let's not get into that. That actually would be more, not events, that would be series of things. Then you would start talking about, like if this happens, then this can't happen, but it could happen the other way around. Let's not go with it. We're just talking about single events. Okay. And then there's, yes sir.
So if you're talking about dogs and cats, it would be like a dog, cat?
Yeah, let's stay out of the world of cartoons. And just in the real life, unless there's, let's also just stay away from mad scientists and whatever. If I'm holding a dog in my hand.
So like dogs with A and then
Yeah.
cats with B.
So is there an animal that is a dog and a cat? No.
So that would be.
That would be mutually exclusive. I love it. So mutually exclusive means if you're one, you cannot also be at the same time the other. Right? So kings and hearts are not mutually exclusive because you can have a king that is also a heart. Not mutually exclusive. They don't mutually exclude each other. Cool. So the picture for this, if you like visuals, here's A and here's B. There's no intersection. They don't meet. Whereas if I'm talking about kings and hearts, they do meet. What's in here? King and hearts. Cool. So they do overlap. They're not mutually exclusive. They don't say, get the hell away from me, right? They have something in common. Okay, and I think the other one I talked about already. Anybody remember what independent meant?
Yes.
And actually, I'll give you a test for independence. Here's a test for independence. So, what did independent mean?
It meant one doesn't affect the other.
I love it. So if one happens, it doesn't affect the chances of the other one. Right? So like if I told you I have a club in my hand, it's still the same chance as the king. We did that one. There's still 1 out of 13 chance, and that's exactly what it was before I told you anything about the card. You with me? So a king and clubs, those two events, would be independent. They don't care about each other. You tell me one, the other guy said, I don't care. The probability is the same. Whereas if I said, well, I have a face card in my hand, now the probability is the king has gone up, right? It's increased. You with me? So those king and face card would be dependent. Depending on if you know one of them, it's going to change the probability of the other one. That's why the name makes sense. Thank God. So the test for independence written in Mathish is this. I guess I have to put a little, if the probability of A given B is the probability of A. Now that's exactly what we just said in English, believe it or not. Yeah.
So an example of this would be like the last class, when you used the card example of the kings and probability, you said, is it a heart? Like, is the card a heart? And your chances were 4 out of 52. And then when you said yes, it was 1 out of 13 to 4.
And they're the same probability.
So would those be independent?
So those would be independent.
Okay.
One happening did not affect the chances of the other one. Whereas, remember when I said, just got off a Harley motorcycle, the probability as a man suddenly went up. I'm not saying it's impossible for it to go when there are women that drive those, but the probability as a man just went up. So those would be dependent.
Okay.
Cool, I love it. And this is actually a huge idea. This is kind of importance you're looking for a certain type, like you're looking for oil, and you know a certain type of soil has oil and they're more likely. Well, when you test the soil and you go, there's some of that soil here, the probability there's oil there just went up. So you'd be more likely to drill there, right? And this is actually a true thing. So this happens all the time, this kind of idea of conditional probability. When I see this, the likelihood of this changes, right? And of course, doctors use it all day. They run tests. Well, the probability you have this has gone up because your test result is positive for you, right? We see these conditional probabilities all the time. So if B happens and A doesn't change, do you see what that says? If the probability of A given that B happened is the same as what A was before, then they're independent, right? A didn't care. B happened, A's not, I don't care. So this would be independent. A and B, independent. So that's a little test for independence. So what do you do if on a test or a quiz, I ask you, are these two things independent? You do this. You do this and you see if it's equal to this, and if it's not equal to that, then obviously they must be dependent. Yes, cool, yeah.
Can you explain what those variables mean again?
These could be any events. They could be like king and heart. They could be like dog and cat, right? They could be any event. A and B could be rolling a 5 and flipping over a chair, whatever. They could be any event that we're talking about.
So if we go back to your card example, and we asked if it was a face card, and they said no. I mean, if we asked it, oh no, never mind.
Okay. I think real quick. Last time, does somebody have the notes from last time? I had a real quick little table, right? It was like men, women.
Oh yeah, I have it.
And it was Mitt and Barack.
And Paul.
Oh, and Paul. Don't forget Paul.
And
42, 42,
42.
It was
48,
48 for all.
48. No, 42, 48.
But you had
Three.
it back.
Oh, I had Barack first?
Yeah.
Okay, let me do that. Obama, Romney, and Paul. Okay, cool.
42,
42.
48.
48.
3,
3.
9, 3. This one.
You did the
51,
sum at the end.
51, 51,
51.
41, 41,
41. Okay.
2.
Okay, gotcha. All right, I like it. And then we added these up on the outside.
Yeah.
So 93,
89,
89, 5,
18,
and I think I happened to get
93,
93
93,
again here.
94,
I didn't
94,
want to, but oh well.
94.
94, so 187. Okay. So watch this. What's the probability that I pick somebody and they want to vote for Romney?
They,
89 out of 187. So what's the probability I pick somebody that wants to vote for Romney, given that they're a man? What goes in the bottom now?
93.
Yeah, 93 men. Cool. 93 men. And out of those, how many want to vote for Romney? 48. So to do this, if I ask you, are voting for Romney and being a man, are those independent events? In order for that to be true, these two must be the same number. So what is 89 divided by 187? 0.4 something.
0.4759.
0.4759, so we'll just say 0.48. Well, let's do 0.476. And what's 48 divided by 93? That's going to be over 0.5.
0.516.
Okay, cool. You with me?
Yeah.
And this is actually kind of, it's not exactly true, because obviously I just made these numbers up out of nowhere, but I kind of was trying to keep with trends that I know. If you're a man, it only increases the chances you're going to vote for Romney, right? And that, of course, is something Romney's trying to take care of right now, is how to bring the women vote back in. Because if you're a woman, it's going to decrease the chances you're going to vote for Romney right now. You with me? I'm not saying that no women will vote for him. We're just talking about likelihoods, right? So are voting for Romney and being a man, are they independent or dependent? Dependent, because one happening changed the chances of the other one happening. So this would be dependent. Yes, sir.
Would they be codependent variables in the sense that like Romney would have to exist to be voted
Yeah, the
for?
nice thing is it works both ways.
Yeah.
if one direction changes, the other direction also must
Right.
change. Yeah.
Because if there wasn't Mitt Romney, there would be no votes for Mitt Romney. In that sense, right? And then obviously you need men and women too.
No, well, to turn this around, you could say the probability of being a man given that you want to vote for Romney. So if I said, yeah, next door there's somebody's gonna vote for Romney, and I had to guess, I would say, oh yeah, it's probably a dude. Because that probability is gonna be higher that it's a dude than it would be a woman. You with me? So we could turn this probability around, right? I'd have to recalculate what it is, because the numbers are gonna change. But certainly, we could look to see probably a man versus probably a man given Romney. We can check that out. Yeah.
Last time we did a probability of man and Romney, I don't know what that means, but it was like 48 out of 187. How is that different?
Because that's an and. Probably a man and will vote for Romney, right?
Yeah.
So then I have to include all those people, and that's where you have to be careful about not counting, double counting. The only time the bottom changes, why is this one 93?
This is only one.
Because it's a given, right? If they give me information, then I have a lesser amount of things that could be true. If you told me the card is red, I have less cards it could possibly be. My denominator is going to change.
Can you do one that's independent? Can you show an independent?
Oh, now, in real life, and this is why the idea of independence is given a little leeway in real life, because it's really difficult to have something truly independent in real life. Cards we can do easily, but cards are sort of manufactured, right? Obviously, I mean, physically, but they're sort of, the situations are sort of made up. So I can, what's an example from cards that are independent? Kings and clubs. But that's not real life. You with me? That's freaking playing cards.
That's assuming with replacement for the card.
Exactly. Right? If I do it without replacement, then everything goes. Now, if I'm picking more than one card, that's what you're talking about. Let's not go there. In real life, if these probabilities were close and turning it around, they're still close, they could be considered independent if it was close enough. So there are some leeways given, because in real life, when I take a sample, just taking a sample, some of these numbers might go one way or the other, depending on how my sample was chosen. Are you guys kind of with me? Okay. So there is a little leeway given for independence. But the nice thing is, we're going to deal with absolutes right now, because we're just getting into this. So it's either independent or it isn't. Yes?
So would it be independent if all the male votes and all the women votes were equal? Like if it was 40?
It would be a really cool bonus question for me to ask you. Create a table where there are some truly independent events happening.
Uh-huh.
And all you got to think about is the ratios have to come out the same, right? You have to design your numbers, and you can do it very intelligently. Some just have to be multiples of the other ones so that the ratios all come out the same. If you don't have a clue what the hell I'm talking about, it's fine. I said that would be a bonus problem. Don't freak out. But if you're curious about the math of it, you could design something that would have independence in it if you were smart about the numbers you were putting in. The ratios just have to come out the same. Wouldn't be overly difficult. Okay, how we doing?
The answer or like the bottom of
Say again?
the ratio, like the answer or like
The ratio of these two. Yeah, this ratio
the
here.
answer.
This ratio and this ratio would have to be the same.
Like
So if these ratios are the same, then obviously this is the same number. Yeah. Okay. All right. One last little thing, and then I want to give you some practice problems. I think we did a problem the other day, which is perfect, the O-ring thing. Remember the O-rings on the shuttle? Yeah. And I said there was like so they're all in a row here. There was like I can't remember now, there was like a 1% chance it was going to not work. Is that right? Mm-hmm. So it's like 0.01, 0.01, 0.01. And of course, if I want them all to fail, that means this guy fails. What's the magic word? And this guy fails, and this guy fails, and means what? Multiply. So then we multiply these together, right? I think maybe I just had two of them. I can't remember. You guys kind of with me here? So here's a cool question. This is actually sort of like one in the homework. Let's say that guy that has 2 alarm clocks going off so that he doesn't oversleep for his final exam. Right? If one alarm clock by itself has a 97% chance of working, you with me?
Yep.
So in that case, if you just use one alarm clock, what's the probability that you won't make it in time to the exam? It probably won't make it is 3%. Now, here's where things get more interesting. That should be a very simple question. Here's the thing. Now, the minute I introduce a second alarm clock, exact same type of alarm clock, it's got the same chance of working. So now I have 2 alarm clocks. 97% chance success. What's the probability that they both work? So what's probably the first one works and the second one works?
You multiply. You multiply by.
Yeah. The first one works and
Multiply.
the second one works, right? You with me? Now, why wouldn't you, I don't want to get too deep into this, but this 97% is not automatically mean it's 97 out of 100, so you got to make this one 96 out of 99. Why does that not make any sense? How many times are you going to use this alarm clock? Probably more than 100. You with me? Let me say that again. I'm going to use this alarm clock a lot. So over all those times I use it, there's a 97% chance it's going to work. So I can assume that, and I'm only using 2 alarm clocks, right? I'm not even using one many times. So there's no reason. These are independent events, aren't they? If the first alarm doesn't work, does that suddenly make the other guy go, oh, you didn't work, screw it, I'm not going to work? Is it going to affect the other alarm clock working?
No.
Now, one little thing I could hear argued is, well, if they're both plugged into the wall and you have your power go out, then there you go. But that was a third thing. You with me? This guy does not affect this guy. So I can just multiply them directly. Right? They're independent events. I can just multiply them directly. I don't have to change this number, do I? Like we did with the 3 out of 51 kings. I had to change that because I picked one king already on the first go. You guys kind of with me here? No? Okay, that's right. And means multiple. So what do you get here?
94%.
About 94? Be a little more specific.
94.09.
Oh, really? Cool. 941. All right, now here's where it gets really interesting. What's the probability that at least one fails? Bless you.
Thank you.
You got only 97%.
Wait, would it be?
The other fails.
3% times 97%?
Say again?
Would it be the 3% times the 97%?
All right, so now here's the thing. So the first alarm clock could fail and the second one works. Or, shit, is that the only way that at least one could fail? The first one could fail and the second one could work, or
Both.
they both fail, or the first one works and the second, oh, yeah, that's, you start to see how if I put like 5 alarm clocks, this kind of question would be stupid difficult if you didn't do it intelligently. What did we just say earlier about at least one?
Always one.
It's 1 minus the probability of 0 fail. Or another way to say none fail is both work. Don't we already have that probability?
Yeah.
Let me make sure you guys are semi with me. At least one fails. How many ways is there to do that? 3. The first one fails, second one works. The first one works, the second one fails, or they both work. I mean, fail, sorry. You'd have to add all those probabilities up. That's a lot of calculations. If I put 5 alarm clocks and it's at least one fails, holy shit, first one fails, the last 4 work. The first 2 fail, the last 3 work. The first one and the last one failed. Oh, screw it. Holy shit, there's a lot. That list is huge. So thank God, anytime I see the probability of at least one something, I can do 1 minus the probability of none. One calculation always. This comes up so much. Yes, sir?
I tried to do the probability of them both failing, which would be 0.03 times 0.03. And the calculator gave me 9
9
minus
Yeah,
4.
it gave you 9e negative
Minus 4.
4, yeah.
Right.
Which means 9 times 10 to the negative 4.
Is that what that means?
Scientific notation.
Oh, okay.
So 0.0009. So if you get that on your calculator, that's what that's trying to tell you. Well, let's do this. This is easy now. What's probability of none fail, otherwise known as both work?
0.59.
Now I just have to do that subtraction.
0.59.
9. Yay. So that's where probability at least one becoming 1 minus none saves your ass so much. Right? If I said 3 alarm clocks and at least one fails, then it'd have to be, I could do it like this. If I had 3 alarm clocks and I want at least one to fail, let me see if you guys are cool with this. So the first one can fail and the second 2 work. You guys good with that? Me writing it like that?
Yeah.
Or means add. WFW, or WWF, or WFF, or, do you start to see why that's insane? I think that is a yes. Right, and then imagine 5, no way. So no matter how many alarm clocks I throw at you, if I ask you that at least one does something, it's going to involve one calculation if you just do this. Yeah.
Now, would you need to put in, I mean, like, if you were, for whatever reason, forgotten or failed to do the 1 minus none, would you have to put it in for each individual one? Would you have FWW and WFW, would you need to do each of those when it's just one of them out of 3 failing? Does that make sense at all? What I'm asking?
I sort of. If I said at least one fails, I'm not being specific about which ones fail.
Yeah.
So I do have to cover every single
Well, I
possibility.
mean, wouldn't there be like a way to like multiply or something?
Yes, it would be. And we're getting there.
Okay.
Yeah, that'll be the next section. Even then, you can't combine them all. There's still several situations. Some of them are combinable, yes. So, let me just give you this here in the last few minutes. I think what I'll do is, I give you this now, basically do just like a practice test. It's the one practice quiz I give you, just because this probability quiz is a little bit heftier than normal. I have the answer key, but I'll give it to you next time. So I want you to try these out on your own, and then bring them back next class. Yes, you have to do this first. This is really not the same situation. I'm not talking about, there's no way I could say none or at least one. You know what I'm saying? This is less, this is more qualitative data. I can't really do the same kind of thing over there. So over there, it's more, what I mean by qualitative, like 0 could work, 1 could work, or 2 could work. So the probability that 1 works out of 2, right, I have my 2 alarm clocks. Well, it could be the first one works and the second one fails, or the first one fails, second works, or they both work, right? But the better way to do it is say 1 minus probably none, which is 1 minus they both fail. Then you'd have to do that. And so like for this problem, this is different from what we did. This is actually the more interesting question. Probably at least one works means the probability you'll actually make it to class one time. You'd have to do this. They both fail, and that would be the 0.03, 0.03 to 0.009. And then, so the probability at least one works would be 1 minus that, which thank God, if I put 2 alarm clocks, my overall probability of success should go up. So it was 0.97 and now it is 0.991. So that makes sense, it's gone up. Whereas if people, if they say, well, it's probably at least one works, and they give me like, they use this number, that doesn't make any sense, it's lower. My chances of waking up should go up now, because I'm kind of covering my ass for what might happen.
Does it ever say at least 2?
It could.
So do you change that 1, or is it always a 1?
Where am I at?
That 1, like 1 minus P0?
Yeah, if it said at least 2, then it'd have to be 1 minus none or 1. So you'd have to add none or 1 together and then subtract it from 1. So basically the probability of something is 1 minus the probability of everything that first thing left out. So at least, probably at least 1 leaves it, the only thing it leaves out is 0. The probability of at least 2, what's it leave out? 0 or 1. So you have to do 1 minus everything it leaves out. Cool.
I didn't get that thing.
Oh,
Or test corrections? Did you also do it by the next session?
due by the next test. Yeah.
Homework also? Or?
Homework's due by that day too. Yeah.
Okay, then you have one question I wanted.
Yeah, sure.
Also, did you pass back the last homework?
I am in, I think I have a couple of things here. Let me see. No, so I'm still in the middle of grading some stuff, yeah.
You finish with that.
Yeah. I went to a conference this weekend.
No, no problem. But just to remind you, no? So that.
Don't worry, don't worry.
Otherwise,
It's on my list of things.
Yeah, yeah. I have no problem with it. Last night I used the YouTube.
Oh, yeah?
Ah,
You found it?
And that helped me a lot.